So it's great to have Steve Collins. He is from Stanford, but he originally graduated from Michigan and then did postdoc at Delft. And he spent 7 years in CMU, and then he recently moved to Stanford. How many years? 3 years?
2 years, yeah.
Yeah. So
just 2 years now.
yeah, he's been like expert and the world leader in exoskeleton and like prosthetic ankle. He developed like one of the best efficiency ankle for prosthetics and published a bunch of science in Nature. We're gonna see what he's up to recently. So let's get started.
Thanks. Great to be here. And thanks Sangbei and Alberto for organizing this visit. It's been really nice to catch up with people. It's been a few years since I've been to MIT. The central societal problem that has preoccupied me for the last 17 years or so is this. There are hundreds of millions of people who are unable to get around effectively, whether it be as a result of disabilities arising from amputation or stroke or just aging, or people who operate under very arduous conditions like these aid workers in Africa. And so what I want to do is design robots that you can wear on your leg to improve major functional outcomes in mobility like energy economy, speed, balance, and comfort. And especially for folks like this. Now, when I was a younger researcher, I thought that because I was good at designing these passive dynamic walking robots, and armed with a little bit of knowledge of human gait biomechanics, I would be able to make exoskeletons that gave people superhuman performance. And I was wrong. This problem is way harder than I recognized. And as an illustration of that, of the thousands of devices that have been designed for these purposes, still only 10 or so have demonstrated an improvement in performance for the person using them. And I think that the problem has been, at its core, that we do not know what the device should do to assist the user. And this is because people are highly complex in our bodies and in our brains. Each one of us is unique, so what helps me might make things harder for you. And we're all constantly changing, especially when we're learning to use some new device. And so these things severely limit our ability to predict a person's response to some new device based just on our intuition or observations from biomechanics or the available models. And slowing us further, we have typically tested our ideas using specialized prototypes that are product-like. And each one of them takes a couple of years to develop. And then, because it's so hard to predict a person's response, mostly they haven't worked. So in the last few years, an alternate approach to this problem has been emerging, and I think it shows very positive signs of being more efficient and effective. And basically, the idea is that if our predictive tools are ineffective for design, then we're really in an iterative and evolutionary process. And so we should focus on speeding and systematizing our search for effective designs. And so we've been developing two sets of tools to try to do just that. One are versatile hardware systems that we call universal device emulators, and the other are algorithms for human-in-the-loop optimization, which are intended to allow efficient navigation of this vast space of potential assistance strategies. This is a schematic of a typical universal device emulator. The person wears a lightweight instrumented end effector that is tethered to very powerful off-board motors and computers. And that means that we're almost never constrained by the power or responsiveness of our hardware. We can test anything we want. And this allows the user to experience a wide range of devices without the overhead of building a physical prototype. This is sort of like virtual reality for your leg. You can program any hypothetical design into the emulator and have an experimental test of what you care about, which is the person's response, in days or even minutes rather than years. And then once you know what your device should do, your cool product should do, you can make that autonomous device armed with a knowledge of how the person is going to respond. Another cool thing is that once you've got this off-board motor control stuff figured out, it's relatively easy to make new high-performance end effectors, like this ankle-foot prosthesis that has independent control of plantar flexion and inversion, eversion torque, which we're using to study balance, and this hip, knee, ankle exoskeleton that we're using to study assistance under a variety of very challenging conditions. Now, there are limitations, of course, to this approach, primarily that you're confined to the laboratory space. And the main implications of that are a limitation on the exposure you can give people to your device and the kinds of environmental variations that you can apply. But I think that we're still in a phase in these types of devices where there are lots of questions that we need to answer even in a controlled environment, like walking on a treadmill in a laboratory. And under those circumstances, this emulation type approach it gives you very high versatility. And fortunately, these devices are getting more accessible. So one of my former PhD students, Josh Caputo, has started a company, Human Motion Technologies, and they are commercializing all the emulator technology we develop in the lab, and right now selling it to research groups. And so far, they're in about 12 laboratories around the country, and this is allowing people who have really good ideas about what assistive devices should do, but maybe not a robotics background, to try their hand at designing new devices, which is exciting for me. And in the long term, the vision of the company, and we're collaborating a little bit to try to achieve this, is to put these systems in a clinical setting so they could be used to improve the prescription process. So people can physically trial different devices before they're made and prescribed to the person. Okay, so now we have these hardware tools. We can try lots of things, but there are so many different functionalities that might be helpful. So how do we navigate that space? Well, I think what we really want are methods for automatically discovering generically effective assistance strategies and customizing them to an individual person's needs and continuously adapting with the person as they grow and change. And one way to do that we're promoting these days, and I think is quite effective, is human-in-the-loop optimization. The basic idea is that you have a person interacting with some device, and while they're interacting, you measure their performance. And then you feed that information back to an optimizer that then systematically varies device behavior. And this, when you look at this diagram, it might sound kind of obvious. But actually, almost all traditional design of this class of devices is operated on the left-hand side of this diagram. Given some desired change in human behavior, there's an implicit assumption that we know what the device should do to achieve it. And unfortunately, that's usually been wrong. We usually haven't known. And that's been a problem. And just to be really clear about this, when I talk about this approach, I don't mean kind of tinkering or hand tuning, which we found to be a lot less effective in our experiments than a systematic approach. And I'm not talking about optimizing some intermediate or device level outcome like mechanical work or kinematics or something. I'm talking about the thing that we really care about for the user, like energy economy or joint load or comfort or something. So optimize the thing you care about. Now, this is not itself an easy task, right? These measurements are noisy, they're time varying, and each one is very expensive in human time and money too. And so we can only get a few objective function evaluations before the person gets tired. And so most of the optimization techniques that work really well in simulation don't translate well to this domain. But we have recently made some progress. And in specific, I want to talk about this approach for identifying the exoskeleton characteristics that minimize metabolic energy consumption during walking. And what happens is you have a person, I'm going to use this awesome, I feel like I'm in the 50s. You have an exoskeleton worn by the person, and it applies assistance defined by a control law, which periodically changes. We then estimate steady state metabolic rate in the person by fitting a first order dynamical model to a few minutes of transient respirometry data. After we've evaluated several control laws that form a generation, we use an evolutionary strategy, in this case CMAES, covariance matrix adaptation evolutionary strategy, popular in the graphics community, to generate a new set of control laws to evaluate and a new estimate of the optimal parameters. We go through this whole process a few times until we feel we've converged to the best parameters. In our recent experiment, we optimized ankle assistance that was characterized by 4 parameters. So we have ankle torque as a function of time. This is normalized to stride period, so this is heel strike through back to heel strike. And we set the peak time, the time that a peak occurs, the rise time, and the fall time of the torque, which allows a wide variety of different patterns. And we applied torque using one of our emulator systems, worn on one ankle by 11 participants as they walked on a treadmill at a typical speed, about 1.25 meters per second. And then after we had identified our estimate of optimal assistance, we performed a separate validation trial in which we presented the optimized assistance pattern, a zero torque mode, where the exoskeleton does nothing, and a few other things, and in a double reversal to get a good measurement of the effect of optimized assistance. And the main outcome of this study was metabolic rate. And what we found is that optimized assistance improved energy cost for all participants, with improvements ranging from 14% to 38%, with an average improvement of about 24%, which is a very large improvement for these kinds of devices. And it's just to put it in context, this is 4 times better than the best results we'd had from hand tuning assistance with the exact same hardware. So that's a really big change in performance through this systematic approach. And just to be precise about what this is, let me say that this is we're talking about the benefit of turning on assistance. So that the gray bar is wearing the device turned off. Really what you care about is the net benefit of putting the device on and turning it on. And of course there's a cost in putting the device on because of its mass and interference with normal movements. And those are not captured well by our emulator, both because the motors aren't on board and because it's over-designed for these optimal trajectories. So to really understand what the net benefit is, you have to make a mobile system that embeds the functionality, which is something we're working on right now. But however whatever your desired outcome, you still want to try to maximize that benefit. And this kind of algorithm is a great way to do that. These are the optimized patterns of assistance. And you can see that some features were really consistent across participants. For example, the timing of peak torque occurred over a very narrow range, whereas some outcomes were more variable, like the rise time. And that suggests that you may be able to get a substantial portion of the benefit with a generic controller that captures, say, those consistent features, but there still may be some benefit to customization. And I'll tell you a little bit about some ongoing work where we're trying to tease out those contributions in a minute. Also note that these patterns of assistance they don't correspond to the best match to biological ankle torque. And they don't correspond to the largest positive mechanical work or power from the device. And that means that you would not be able to guess these based on biomimicry or simple thermodynamic interpretations of the task of walking. The optimization approach is necessary to get there. Okay, so just to summarize this design philosophy, people are really complicated. So most things we try in this space are going to fail. And so we should use versatile hardware so that we can fail quickly and move on to the next thing. And we should use a systematic searching approach so that we can search that space efficiently. And I think our group's doing this. Connor Walsh's group is doing, David Remy. And if I hear other people talking about incorporating these kinds of methods, and I'm really excited. I think that this is going to speed the development of devices that truly enhance performance for the users. And I think it's an exciting time to be in this area. We're like maybe 15 minutes into the talk. An hour is a very long time to stand here and just talk at you. So why don't I pause here and answer some questions? Yeah?
You're basically doing some sort of derivative-free optimization. Hold on.
Yes.
So you're basically doing some sort of derivative-free optimization. So
Yes.
you had a really nice, really low-dimensional hand-designed sort of controller space that you were searching over here with only 4 parameters.
Yes.
So I guess my question is like, how many? So in the upper right, you have like 6 points you measure. Like, how many do you need to do before you're going to take a step and measure the next ones? And then, that involves each one of those. You have to run the person, and then how does that relate to sort of how low-dimensional, with your sort of knowledge, you designed the policy?
Yes, that's a great question, and I can tell you a little bit about the theory here, but we shouldn't put too much weight behind it until we have borne this out experimentally, and that's something we're working on. So, first of all, the number of control laws per generation that you're recommended to use scales with the log of the dimension of the parameter space. So, which is good scaling for these kinds of problems. And I'll tell you a little bit more about some of our ongoing work later, but we're seeing that the time to convergence, which depends both on the number of control laws per generation and the number of generations that you need to evaluate, seems to scale more or less linearly in the number of parameters in the tests we've performed so far, but it's very early. And then I just want to also say, yes, it's derivative-free, which is nice because the data is really noisy. Another nice feature of this approach is that the main component of this, which is updating your estimate of the optimal parameter values, is memoryless. So that estimate is made after each generation independently. And this helps because the person is changing. So that first generation, their response to a really good control law might be really bad. And if you're doing something like trying to characterize the landscape using, say, a Bayesian approach, and you don't modify the method to downweight old data, then you get these conflicting signals, and you may quickly eliminate something that would actually be a really good assistance pattern. Yeah, Harry. Oh, sorry. Songbei's in charge, so yeah.
So Steve, quick question. You said that when you look to the biological data, it doesn't fit. Do you think it's because the emulator doesn't represent well, that is general enough, or how do you attribute that? Why are you finding gains that do not match what humans had by evolution found? Yeah,
so that's a great question. So, that's a great, it sort of implies this philosophical question, right? And so let me launch into that reel. So when you change the plant, as you do when you add an exoskeleton to the person's body, you might naturally assume that the optimal trajectories for that plant have changed as well. And especially if you change like the relationship between movement and cost, or cost in a very broad sense, right? When the exoskeleton does mechanical work on your leg, you don't pay for it in metabolic energy, for example, right? And there are some other important differences between the human body and the exoskeleton. For example, at this phase of the gait cycle, your ankle is plantar flexing with high velocity, And when muscle is contracting at high velocity, its efficiency decreases greatly. So there's this force-velocity relationship that's done for a given amount of activation. You get a much smaller force when the muscle is contracting fast. So we think actually that what we're seeing here is maybe these complementary strengths between the person and the device. It's doesn't cost you too much to produce ankle torque early in the stance phase when you're stretching tendons and maybe slowly lengthening the ankle plantar flexors. But late in the stance phase, when the ankle is moving quickly, the muscle is not very good at doing work then. But maybe if you could get that work for a reasonable cost, you would like it. And the exoskeleton can do that. Does that make sense? Because it doesn't follow that same relationship. That was a little bit of a meandering answer, but basically I think whenever we change the person's body, amputation, exoskeleton, anything else, our default assumption should not be the best thing to do is to do what the person originally did. Our assumption should be there's some new thing that's best, and we have to find that.
So when you're using the covariance matrix adaptation, that's necessarily, within each population you have kind of randomized points. Do you do anything to kind of rein in how random each controller is from the previous one, so it's not super jarring to the user?
That's a great question. So far, we have mostly been using vanilla CMA, but I think so that would be better. Yeah. No, I mean, and we see this sometimes. You can tell when somebody draws a bad generation, right? The mean's here, and you're only sampling 8 points in this parameterization. So what if they're all over here? Ooh, this is not good. And that can set you back. Since we can only go through this loop. I mean, in this first experiment, we went through 4 times so that we could have a one-day protocol. In our more recent work, we're going through more times, but it's still very few generations. And so having one bad generation, it doesn't matter too much in a computer simulation, but in these experiments, it's really costly. So yes, forcing some distribution, or there's some trade-off. That if you keep it truly stochastic, this helps you avoid getting stuck in local minima and things like that. But in our case, I think, yeah, we should be embedding some of our knowledge about good directions to search. And we haven't done that yet. Yes?
So you talked about, so there's some sort of parametric representation of your controller space that you're searching over,
Yes.
and that's maybe based on intuition or knowledge.
Yes.
And
yes.
or just what the ankle can do, right? And so when you get results, some of these things have greater effect on metabolic rate, others don't, and kind of you pointed that out. And so
Yes.
have you thought about changing the design of the ankle based on this in either a systematic way or more of an intuitive way? And I know it's a hard problem, but
So first, let me just reiterate something you said
yeah.
in slightly different words, which is, in order to form the parameterization, this is where observations from biomechanics and our intuition and simple models come in, right? So we still need those things, and it's for setting up these problems. And obviously, if you set up the optimization problem badly, you're going to get a poor result, right? And then you also noted that perhaps a conclusion we could draw from the result is that some dimensions don't matter, and some do. And I think that is a possibility. But I don't think we have sufficient information to make a strong statement about that yet, because you can't differentiate between dimensions that don't matter and dimensions that do matter, but over which there's large subject variability. And so that real way to answer that question is you have to do another experiment in which you pick a reduced dimensionality representation of the assistance pattern and then optimize and then see how the optimal assistance result changes or doesn't. And if it doesn't change, great, big win. Yeah. Right on. And just one other thing about the constraint, potential, like, is it possible that the reason we don't get biological torques is because of hardware limitations? The bandwidth of the system is like 15 to 20 hertz, so the closed loop torque bandwidth, which is a bit higher than for human muscle at the ankle joint. So we think that's not a limitation. In fact, one of the things we find is that we have to place an artificial limit on how late this peak occurs, because the optimizer tends to push it later and later, and people don't like it when it's late, but we can still track really sharp trajectories there. Okay, so that's sort of the philosophy and a very clear, coherent story. And now we'll go to current work, where things are a little messier and ongoing. And I would encourage you to please just jump in with any questions you have or thoughts or disagreement as we go. So I want to talk about a few different directions that we're moving in right now. One is trying to better understand why this optimization works and how it interacts with learning. And we're trying to apply it also to new devices and new activities and new objectives and to people who have disabilities. And then finally, we're trying to translate some of our effective devices outside the lab. So going back to the study I mentioned a minute ago, one of the things that we realized quickly is that while we initially expected that what we would do is tune device properties to match the person, at least equally important was helping the person to learn how to use the device better. So here's a participant walking with no exoskeleton. Here's the device in 0 torque mode in one of our experiments. Now we're going to turn on torque. This is a good pattern of assistance, but you can see the person looks pretty awkward, right? There's a lot of upper extremity involvement. And then this is a very similar pattern of assistance after optimization during the validation phase. So clearly, a lot of what's happening during this process is in the human side of the system. So to try to better understand the role of training in these tests, we've performed a follow-up experiment. This is work led by Katie Poggency, who's a PhD student in our group. And what she did is to bring in naive participants and expose them to optimization on repeated days and then validation on every day. And so this is days on the x-axis. On the y-axis, we have the change in metabolic rate compared to the 0 torque mode. So you can see down is good. That's bigger improvements. And we applied 2 different patterns. One is this generic assistance pattern that was the average of the best patterns from a different experiment, and this red pattern, which is the subject-specific optimized assistance pattern. And what you can see is, for many participants, energy cost is dropping through 4 or 5 days of optimization, so 8 or 10 hours of exposure to the device, which is a very long time. And if we look at the energy cost on the first day, we see that if we just give the person the device and measure their immediate response, there's almost no benefit. But after a complete round of training, and there are 3 different groups that I'll explain in a second. So this is the continued optimization that I described before. That generic pattern of assistance after training gives you something like a 30% improvement in energy economy. And optimized assistance gives you almost a 40% improvement in energy economy. This is just assisting the ankles bilaterally, which is, by the way, a very big number for us. We're very excited about that. But we kind of thought that something about the experience of this optimization might help people learn how to use the device. So we tested a different group. They just saw that generic pattern over and over again. Very, very boring protocol for them. 10 hours walking through this. But it turns out that their response was almost the same. So we think that their level of expertise at using the exoskeleton was really similar. It's kind of independent of that variation experienced during optimization. Yes, sorry. So the static group, so each of these is 5 individuals, all naive. And the static group just experienced the generic pattern of assistance over and over again. So it's the same duration of exposure, but instead of undergoing this optimization where we try this control law, then this one, then this one, then this one, they just get the same thing all the time. And
is the static one closed loop?
It's closed loop in the sense of the torque control is closed loop, but we're not doing human loop optimization. We're not doing any optimization. They just the same thing all the time.
So it's not wandering position to feedback to torque?
So we're doing closed loop torque control. So they're getting a consistent pattern of torque and time as parameterized, as I described earlier in the parameterization. The thing we're trying to tease out here is, we know in motor learning literature, sometimes variation training is really important to acquiring expertise. And so we thought that that variation in device behavior might be helping people to learn how to use it better, to help explain some of the differences we see with this optimization compared to our previous experiments. But it looks like that's not so important. However, there's another group, this re-optimization group. And the re-optimization group, we reset optimization every day they come in. So instead of sort of starting with this big noise and funneling into something good, they start to funnel and then they start, and it's rough. And so they seem to experience interference in their training because of this high variation. So the type of training seems to matter. You can screw it up, but we haven't figured out a way to enhance it yet. And also this shows us that in our first experiment that I talked about earlier, 1 day was not sufficient to identify the optimal assistance parameters. Okay, so another question that we're curious about is, how does this scale to larger parameter spaces? So this is a hip, knee, ankle exoskeleton that we've started to optimize. And of course, defining assistance requires more parameters. And so in a first test, we've defined it using 9 control parameters and optimized. And what we're finding is that this is the distance between estimates of the optimal parameters over time as we go through the optimization. So each one of these is a generation. And that decreases over time. And it seems like a pretty good measure of convergence in this task. And we can also simulate very, very simple simulations where we approximate the task and person as a bowl in n dimensions with noise. And we get really similar convergence rates. And with this device, we see improvements with optimized assistance of 30%. This is all hot off the presses, n equals 1. But it's only 30%. So that tells us that we probably didn't parameterize the problem well enough. And actually, since just in the last couple weeks, the students who are leading this project, who are Gwen Bryan and Patrick Franks, have completed individual joint optimizations with a richer parameter space and found that we can get better than 30% just assisting the hips or just assisting the ankles. And we get something like 15, 20% just assisting the knee. So that's a strong indicator that we need to free up the constraints here and operate in a higher dimensional control space. Yes?
I know you haven't done this since it's so new.
Yes.
But what's your intuition in terms of individual joint optimization versus when you put all those optimizations together? Like, would you need to do a different optimization for the full joint system?
That is a great question, and that is something that I hope to have a preliminary answer for in the next few weeks. So we're going to do just that. Take those optimized controllers and just slam them together and see what happens. I don't think it's going to go well, but you have to do the test to know. My intuition is, so just to say something a little more scientific, if you look at estimates of how much, say, the ankle plantar flexors, how much energy the ankle plantar flexors are using during walking, it's not 40%. It's a lot lower than that, maybe 20% or something. So how can you get 40% energy cost savings when you're only assisting the ankle joint? Well, because the changes are not just happening at the ankle joint. The person is changing their whole coordination pattern. There's this global change. And so you're saving energy not just at the plantar flexors, which actually don't turn all the way off. They're still quite active. You're saving a little bit of energy there, and some at the knees and some at the hips. And it's more complicated. But anyways, you get the point. So it's unlikely that these things will add linearly, especially since 40 plus 40 plus 20 is 100. So it seems unlikely. But Okay, great. We're also quite interested in applying this to new tasks, and an obvious starting point is running. So we recently completed an experiment where we optimized the same exoskeletons, same parameterization of assistance during running at a slow speed, about a 10-minute mile pace. So like 2.5 times slower than Kipchoge. And what we found is that, here again, optimized assistance substantially improves energy cost compared to zero torque. And it also, although this is not so meaningful, I think because of the reasons I mentioned earlier, it also improves energy costs compared to normal running shoes by 15%. But this study also illustrates another kind of fun application of human-in-the-loop optimization, which is you can compare the best version of two different design types. So here, in addition to optimizing the powered device, we also optimized a spring-like device, where the parameter space was the stiffness and whether it's how much it was stiffening or softening, and the engagement angle of a spring. So that would be something that you could design into an energetically passive product. And in this case, we found that the benefits were quite modest compared to our powered device. So that is nice. That helps us to know which direction we should pursue for untethered systems. We're also interested in other objectives. So we spent a lot of time on metabolic. And oh yeah, please, yeah.
Is the difference between this passive and the active one just that like the torque to deflection curve is something you couldn't achieve with a spring? Or like could you still take the power, like, or there's just a lot of variability in those curves over time? Or
That's true. The pattern of assistance here cannot be achieved by a passive device. It encodes, so this is we encode torque over time. It's independent of joint state. So, and what happens is that the person is largely dorsiflexing when the torque is low and plantar flexing when the torque is high. So there's a big work loop. This encodes a lot of mechanical power by the device. Does that make sense? So, but the idea here is that you can constrain your optimization in various ways so that whatever you discover can be implemented in different classes of device. Does that make sense? So from passive to semi-active to fully powered, or let's say I have an electricity constraint I want to enforce, then you can put that into the optimization and operate under that constraint. Okay. So we don't just care about energy economy, of course. Oh yeah, sorry. Yeah, another question. Yeah.
So for this graph, like the optimal spring-like torque controller, does it have the same number of parameters that you tuned for the optimal powered controller?
It had fewer parameters, 3.
3? Still 3?
Yes. Okay. So we've now done a variety of different control dimensions from 3 up through 11, and 11. Sometime in the near future, we hope to tackle something more like 20. And that will, they're all n equals, well, actually these are n equals 10, but the higher dimensional ones are just n equals 1, but it'll still give us a sense of how things are scaling. I think implicit in the question is it possible to develop more efficient algorithms for this optimization process? And I think so. And I would love it if some of the people in this room put their creativity towards that problem, because I'd love to use better optimization algorithms. Especially, I think, an intriguing idea is to try to tease out these two separate tasks of training the person and efficiently identifying optimal device parameters. There may be, once you're trained, it may be possible to identify optimal parameters more quickly. Yes?
I was wondering, from the data you have
I'll
here,
repeat the question.
I was wondering, from the data you have here, would you say that it would be difficult to create a passive running prosthesis that resides on the ankle?
So the question is, would it be difficult to create a passive running prosthesis that resides on the ankle? And I would say, of the class that we constrained our optimization to, I feel confident that there isn't a big benefit to be had from such a device. Of course, there are many different ways you could try to contrive a passive running device, and we have had more success with other things like tying a rubber band between your feet improves the running energy economy by 6%. So that beats our fancy exoskeleton emulator. Okay, so energy cost isn't the only thing that matters. We also care about things like speed. And so recently, in work led by Sungmoon Song, who's a postdoc in our lab, we've tried to tackle this. So first, we needed to be able to measure speed while you're tethered. So we self-paced the Vertec treadmill using just local force information. There's a Kalman filter estimating your position of velocity, blah, blah, blah. And it's nice because you don't have to have a mocap system integrated or other measurement devices. And then we validated that self-selected speed on the treadmill matched that overground in a bigger experiment with different overground walking distances and different self-paced conditions and so on. And there's a really strong correlation, which is good. And then we began performing human-in-loop optimization, except instead of optimizing human energy consumption, trying to minimize that, we're trying to maximize self-selected walking speed. And with 9 participants through so far, we see that optimized assistance leads to about a 40% improvement, or increase, I should say, in self-selected walking speed. And this is cost of transport on the y-axis here. We see that cost of transport actually decreases a little bit at that speed. So we're not just like putting people on a forced march. And to increase our confidence, and I'm not showing these data, but we applied a couple of additional conditions, including one where we just applied the generic assistance pattern that we know reduces energy cost. And it did increase walking speed, but just a little bit, about 10%. And we also applied a condition that we expected to make, to annoy people, basically, when they're walking, and that decreased self-selected walking speed. So we think we're finding something that's real here. And I'm very excited about this. And it's, I think a future direction for us is to move on to multi-objective optimization and try to capture all the things that you care about in one cost function with appropriate weights on each for the population and the task. Okay, now that, I told you I got into this because I wanted to help people with disabilities. So what happens when we try these techniques on people who've had a stroke? So we recently applied the same exact optimization process with an exoskeleton worn on the paretic limb of a few participants that have hemiparesis following stroke. They're chronic participants. And unfortunately, what we find is a much smaller improvement in energy economy, about 5% with optimized assistance. And observing the participants' behavior in using the exoskeleton, we have a couple of guesses as to what's going on. And the first is just that all the changes we care about are changes elsewhere in the body, right? That they need to coordinate with the device to get a benefit. So it seems like participants are not making those adjustments to their control pattern that are needed to get a benefit. And so we're trying things like training with biofeedback, setting target joint angles, ground reaction forces, muscle activity to help improve the training process. So far, that's not working very well with, again, very small sample size piloting stuff. Another way to try to address this is by enforcing some of that inner limb or inner joint coordination with multi-joint assistance. And that's something we're about to start on, and I feel more hopeful about success in that approach. Yes?
I'm curious on the increased difficulty in training for stroke sufferers. Do you think that's more likely to do with the consequences of the stroke itself, or perhaps just due to the population that usually suffers from strokes might have more difficulty learning?
That's a good question. So the question is this observed effect, and again, pilot data and all that, but is it about the stroke or about older people who are more sedentary or something? And I don't know, but I think my strong intuition is that it's about the stroke. It's so, right, just I think I said this in maybe slightly different words a minute ago, but the benefits of these devices are derived from changes in the person. And if the person can't change, or if there's strong constraints on how the person can change, or the person can't change quickly, like there's a slow learning rate, say very slow learning rate, then that limits the efficacy of the intervention. So I think what we're trying to do now is change the architecture of the intervention in ways that enable improved performance with less change, or with the right dimensions of change in the participant. Does that make sense? Yeah. Yes, please. Oh, good. Lots of hands. Okay, good. Yes.
I think I have a similar question.
Yeah.
When you set the cost function as metabolic rate, did it always, from feedback from the participants, did they always correspond to more comfortableness?
No. So the question is, does minimum metabolic rate correspond to most comfort? And the answer is no. First of all, people are very bad at estimating their effort. And so a classic example is have a person walk with exoskeleton assistance for a while and accommodate, and ask them if the device is helping them. They say, eh. And they turn it off and they say, whoa, this sucks. So it's a very common observation in this field. And there's also some more careful studies of rate of perceived effort using with assistance that's really changing your effort. People are just not very good at that psychological task. Yes?
Can you speak relative to this slide that we're seeing, the difference that you observe between stroke patients walking on a treadmill rather than overground, and if they use walkers, canes, or daily use devices?
We limited ourselves. The inclusion criteria were you have to be able to walk without an assistive device. And I don't think that the overground versus treadmill makes much difference in this. We give people lots of training on the treadmill. And based on some of our other experiments, I think we're in safe territory there. Yeah.
Do you know if these patients have any sensory deficits that would perhaps also hinder their ability to learn the controller of the device?
So the question is, oh yeah, you have the microphone. That's perfect. Yes, they probably do have sensory deficits, and yes, that's probably in part responsible for inhibiting motor learning.
Do you have any way of thoughts of how to quantify that, or just whether that's the case?
I mean, how to quantify it. So there's a basic scientific question here that you could dig into. You could say, okay, good. People with stroke don't respond well to these devices. Now, let's show why. But I am of a different ilk, and I just want them to work better. I want to increase performance. So instead of, I think it'd be very valuable to the field, but we're kind of seeing this and saying, oh, let's try something different and see if we can find something that works. Okay, so how about amputation? This has been an area of research in our group for a long time, and unfortunately, what we're finding is that strategies for powering the prosthetic limb, changing the average device characteristics in ways that are expected to affect propulsion, are failing. And we have tried literally 14 different architectures, human loop optimization approaches, giving people more time, less time, enforced exploration, all kinds of things with this, and I'm quite confident that it's not working. We've also seen in our lab that if we just sweep, we have different levels of average prosthesis power. This is net mechanical power from the device versus metabolic rate in the person. We see a flat line in other experiments. So we're trying to figure out why that's happening. Now, I think very likely this relates to these constraints in motor learning that we were talking about a minute ago. For example, you don't have proprioceptive information from the foot, and you don't have direct control of it either. Now, I think the most promising intervention, or the most promising technology along this path to solve this problem is osseointegration with a direct neural interface, bidirectional. That's where we have to go, I think. And I know that I spoke with a couple of people earlier today. I don't know if Tony's here, but that are working on exactly that technology. And in 10 or 20 years, I think that'll be really exciting. And when we get those interfaces, I'd love to plug people into our emulator and see what they can do with it. But of course, that takes a long time, and it's a little invasive. So one way of trying to answer these basic scientific questions is partially restore those pathways by teleoperating an ankle with a wrist exoskeleton. And this is work in collaboration with Alison Okamura. So this, the prosthesis is following the angle of the wrist, and the wrist is giving you a haptic rendering of the torque at the ankle joint. This is very early stage stuff, but we're excited to see if that helps people learn how to use the device. And another test here is to see if we put an exoskeleton on the sound limb of people with amputation, can they learn how to use it well? And if they cannot, that might be an indication of a more global limit on motor learning or the available coordination strategies after adaptation. Yes?
Wondering the socket mechanics affects a lot. That's hard to make it stiff, and then whenever change that socket, like skin actually react on it. So basically, what you meant to do doesn't really affect.
So I think that's so the question. So I think that we consider that as a possibility, and so in this experiment, we actually did a careful analysis of the flow of mechanical work through the system, and we see that actually the work is getting to the center of mass, and it's getting to the swing leg, and it's not all just being damped out in the socket. And it's probably not obvious from this figure, but it's a very large amount of work that we're doing with it. It would be hard to absorb it all in the soft tissue. Like this is normal. Okay, this is old biome data, and this is our max. So I don't think that's responsible. But of course, the socket does cause all these other problems like pain, the potential for pain. You got to avoid that, and sure, there is some movement. And yes.
I'm trying to understand this part here because the amputee, he still has proprioception through the socket. So I'm trying to understand why would you get a good result using an exoskeleton on a healthy subject and not get the same result in an amputee. And the sensory part, I'm not
So this
buying.
confused look on your face, I feel you, man. This is like, it reflects, that's my inner face about this problem for like a decade. So yeah, I mean, I would not have guessed this going in, right? We have Matt Hanford here is some nice simulation models that show that theoretically you should be able to get big improvements in energy economy by appropriately powering a prosthetic device, and it just doesn't happen in humans. And it's true that there's some sensory information coming from inside the socket. I mean, but of course, there's a reason that our bodies are just full of distributed sensors. We could theoretically infer all sorts of information by remote sensors or low fidelity, but it helps to actually have sensors at the joint and at that contact with the ground, and it helps to have some connection between sensing and control, and apparently that's important here, it seems like. And the other evidence of this is that here where we apply assistance to the unaffected limb, we do the exact same optimization, and instead of getting, say, 40% improvements in energy economy, we get 5%. So that suggests a more global constraint on either learning rate or the available coordination strategies. Now I see Songbei standing up, and I see that there's 3 minutes remaining, and I have like 20 slides. So what I'm going to do is I'm just going to very quickly, I'm going to give you the highlight reel here really quickly. We're looking at balance, and we've made a new prosthesis to try to study it that has control of the center pressure through these independently actuated toes, and you can do fun things with that center pressure control, including we're trying different ways of assisting people in uneven terrain, which is a very common complaint among people with amputation. So the one success story in this area is the biome, and I think maybe it has to do with balance as opposed to propulsion, and so we're targeting balance. And we're also looking at trying to improve balance in response to big disturbances, like big pushes. So we've made this thing PushBot. We're open sourcing it, and so it's like a couple $1,000 to build one for yourself. and you can really shove people around on the treadmill, and then try to make devices that help them recover. Now, of course, as we find things, we want to translate them to mobile systems. We want to keep things lightweight and cheap, so using as little energy as possible would be nice. This is a device that uses no energy itself, but reduces the metabolic energy cost of human walking by about 7%. And it has a clutched spring, and I won't walk you through all the details, but with the right stiffness, it works. But it has no electrical control, no computer control, so we're making new clutches that combine this very low energy consumption, like less than a milliwatt, and electrical controllability based on electrostatic adhesion. And they have these great properties. For a contact patch like this, you get 200 newtons, a mass of a couple grams for the actual electrode. They use less than a milliwatt of power. They have the low voltage of 300 volts, which for electrostatics is actually pretty good, and you can use conventional electronics. And they switch on and off in about 20 milliseconds, which is quite fast for these kinds of systems. We've put them through millions of cycles without fatiguing out. My former student, Stuart Diller, has started a company. I have no role in the company or the other company I talked about. And they are now selling development kits. So if you want to play around with electrostatic clutches for your application, you can buy one for $100 or something. And we think that these could be used in cool new robotic systems, lots of them, blah, blah, blah. And there's some hard control problems that we solved. And in the right conditions, you can get energy savings in these net zero work cyclic robotics tasks of 50% on average, 80, 90% in the best cases. So we could use these to really improve energy economy in mobile robot actuation. Thank you to my students, and thank you to my sponsors, especially the NSF. And I recently joined Science Robotics. So much cool work going on here at MIT and robotics. I hope you'll submit your work. We need awesome stuff. So please send it our way. Thank you.
Maybe we'll give you one lucky guy to give the last question, because we have a lot of questions in the middle. Anybody?
And I'll hang around and answer any, take all comers as.
So, I guess, all of your works were to minimize the energy expenditure, metabolic energy expenditure, basically.
Or increase speed, or improve balance.
So or increase speed.
And we have some work I didn't talk about improving comfort.
Sorry.
I totally agree. I totally agree. It's not just energy costs. You care about lots of stuff. And that's where we want to get to.
My question's maybe in the same vein. So everything you showed is for periodic motions. How do we, obviously the world is not periodic,
Yes.
so how do we go beyond that?
Totally, we can and we will. And so we start with periodic because it's the easiest. And if you count up the distance walked in a day, most of that distance is covered in steady gait. So that's the first thing to do. But most of the bouts are short and mostly transient. So the way you do that is you repeatedly, over and over again, stop and start up and stop, and then start up and stop. And you do that back and forth long enough that you can get a reasonable estimate of the outcome that you care about, like energy cost, speed, or balance. And then you can apply the same kinds of optimization techniques. Buying it? Maybe? Okay.
All right, thank you very much, Steve.
Thank you.